So we will get started with chapter 16, double and triple integrals. All right, so in this handout, which includes both 16.1 and 16.2, we will define, what we call partial integration, evaluate, iterated, or in general, or like double, later, triple integrals, and some applications to double integrals for volumes, areas, and finding the average value. All right, so first of all, how are we going to go about double and triple integrals? Well, in a similar way we did, what was that, partial differentiation, we will do what we call partial integration, for which we will integrate with respect one of the variables at the same time. In a similar way, we differentiated with respect x, separately we differentiated with respect y, etc., for all the variables we have. All right, what else? So now here is the thing. When we integrate a function that it's potentially some function's partial derivative with respect x, if we integrate it with respect x, constant of integration that appears at the end of integration, it's not going to be just a constant, just a number. I mean, it could potentially be just a number. That's fine. However, since we are integrating with respect x, every other variable out there will be taken constant. That is, if we integrate with respect x, if we have a function of two variables, the constant of integration will be an expression of the other variable we held constant, in this case y, or could be simply a number. Likewise, if we integrate with respect y, what are we doing? We are holding c as the x as the constant, or maybe it could be just a number. Well, so let's see how do we go about partial integration. So let's look at this couple of examples. So the integral of 2xy dx. So in this case, we're integrating with respect x. Let me take everything that is constant outside of the integral. That is, I'm going to take the 2y integral of x dx. And well, we know how to integrate x with respect x. That's going to give us, well, keep the constant 2y times x squared over 2. All right? Or, which is simply going to be divide out, the plus c, okay? And divide out the 2's, that is x squared y plus c. However, the c is going to be different this time. It's not just going to be the letter c. Since in this case we integrate it with respect x, all right? Here this constant, it's a function of y. All right, so that is going to be our final result. All right? Okay, so letter B, the integral of e to the x, y, z. Here we want to integrate this with respect to z. Okay, so in this case, we are going to have two constants here, two variables that will be held constant. That is x and y, because we're interested in integrating with respect z. So number one, let's recall, how do we integrate e to the ax? For instance, the integral of e to the ax with respect x, that equals 1 over a integral of, not integral, 1 over a e to the ax, all right, plus c. So in this case, well, we have three variables in the exponent of this exponential function. However, two of those are constant. That is the product between x and y. All right, so that is, it's going to be, the integral is going to be itself, e to the x, y, z. However, 1 over the constant. In this case, the constants are x and y. And in this case, the plus c is going to be a function that depends on the two other variables that we held constant. All right, that is, it's going to be a function c of x, y. All right. and that's how we integrate partially. I mean, it's going to be the same integration rules that you learned back in Calculus 1 and Calculus 2. All we're going to do is apply them to functions of multiple variables. All right? And of course, I mean, the fundamental theorem of calculus, first and second, both of them can be applied when having functions of multiple variables. And also, so here, we would apply the fundamental theorem of calculus to one variable. That is, that variable that we are integrating with respect to holding the other variables constant. That's how it's going to work here. Okay, so let's evaluate the first integral right here. All right, okay. Evaluate the integral from 1 to x for the function 3x squared plus y with respect to y. So we're not doing double or triple integrals here. We're getting the tools first. How are we going to do the partial integration? Then we're going to put all of it together in a double or a triple integral. Okay, in this case, we're integrating with respect to y. 3x squared, it's a constant with respect to y. So the integral of a constant will be the constant, which is 3x squared times the variable 3x squared y. And then the integral of y, that'll be y squared over 2, or 1/2 of y squared. Now, we're going to integrate this from 1 to x, okay? However, be careful, and I'm going to be highlighting this for the first few examples, or maybe for a while, so we don't lose track of what we're doing. Notice limits of integration are only going to be applied to the variable we integrated with respect to. That is, these limits, x and 1 and x, just apply for the variable y. And leave the x alone. All right? That is 3x squared times x, upper limit, plus 1/2 x squared. So that is upper limit minus lower limit. That is 3x squared times 1 plus 1/2 1 squared. Okay? And let's simplify all this, right? So that'll give us 3x cubed plus 1/2 x squared, and then minus 3x squared. And here what do we have? 1 squared, which is 1 times a half. It's a half, but careful with the negative sign outside. That'll be minus 1/2. And combining like terms, what do we have? A half minus 3, which is a half minus 6 halves. Isn't that negative 5 halves? So that'll be 3x cubed minus 5 halves x squared minus a half. All right. Actually. So the question is, why don't we add the c's, right? So for instance, if I added here a plus c of, what is that? C of x, right? And then plus another c of x. You see how they're going to cancel here? So that's why we need to add those constants. In the same way that when we integrated f of x dx from a to b, that is, we get big F of x from A to B, but actually we omit the c's because it's going to be the same constant in this case, and it's going to get canceled. All right. Okay, so for part B, we're asked to evaluate the integral from y to pi over 2 for the function cosine x sine y tangent z with respect x. So that means we're integrating with respect x, everything not containing x, take it as constant, take it outside. That is, in this case, sine y, sine y, tangent z, integral of cosine x dx from y to pi over 2. Okay, so the integral of cosine is in that positive sign, so that'll be sine y tangent z. The integral of cosine again is sine x, and evaluate this between y and pi over 2. And again, keep in mind that we're only integrating with respect x. That means the limits of integration y and pi over 2 are only applicable to the sine x function, or rather the function containing the x. All right, so let's see. So that is sine y tangent z, and simply do sine pi over 2 minus sine y. And well, sine of pi over 2 is that 1. Okay, sine pi over 2 equals to 1. That is sine y tangent z times 1 minus sine y. Right? Okay, so now that we have evaluated a couple of these partial integrals, now let's put them together into what we call iterated integrals. That is, well, that's going to be this double integrals and potentially, well, the triple integrals and potentially quadruple, quintuple, sextuple integrals. Of course, I mean, there's no limit as to how many iterations of an integral can we do. So, in just the same way we did partial derivatives when we took the partial with respect x, and then with respect y, and then with respect z, or maybe 3 times with respect x, maybe 3 times with respect y. Well, it works the same with the integrals. We can do in the order that we want. Well, as long as it is an integral that we can evaluate. So that's the problem. That's where it can be a little tricky. So, in this case, since we're going to put together double integrals. In some cases, the double integral it's just ready to be integrated. In some cases, we're given an integral in that order that it's simply impossible to evaluate with the tools that we have to evaluate integrals. So we need to do a process called changing the order of integration. Well, that's something we're going to discuss later in the section. Well, in the meantime, let's have a look at this integral that is ready to be integrated. The changing the order, we're going to do that later. Okay, so we're integrating from 1 to 4 and from 0 to x, the function 4xy minus y, first with respect x, and then with respect y rather, and then with respect x. Now, here's the thing. When it comes to a double integral, the way we're supposed to interpret this is, number 1, the inner limits of integration indicate the first differential that we read from left to right, that is the dy. That is, inner limits, inner integral, outermost limits dx with respect x. Those are for the variable that for which we have the integral in the outermost integral. All right. So, okay, let's do the partial integration. So here, number 1, integrate 4xy minus y with respect y. That is the integral from 1 to 4, okay? And then let's just open brackets, the integral of 4xy, which is 4xy squared over 2 minus y squared over 2. And we're going to integrate this between 0 and x. And again, these limits right here, let me highlight them just to stress on the fact that we will be applying those limits of integration to the variable we just integrated with respect to, that is with respect y. So leave the x alone. Okay, so that means that's the integral from 1 to 4. Okay, so 4, let me simplify this. Okay, so that'll be 2 x times x squared minus x squared over 2. Now, here is the thing, guys. look at the lower limit of 0. So, and in this case, notice how if we substitute that limit of 0 to the two terms right here, do you guys agree that it's going to give us a 0 for both terms? Okay, in a situation like this, it's fine not to write anything. Just go about minus a big 0, all right? Dx, okay? Otherwise, if you have a number or another variable or something that it's not going to yield a 0 in the end, write it down, all right? But not for this case. It's fine just to round to 0, to write down to 0. Okay, so what is that? 2x cubed, so that'll be the integral from 1 to 4 of 2x cubed minus x squared over 2 dx, all right? And okay, let's integrate this with respect to x. So that'll be, okay, number 1, 2 x to the 4th over 4 minus 1/2 x cubed over 3 from 1 to 4. Okay, let's simplify this. That's 2 over 4, which reduces to 1/2 minus 1/6 x cubed from 1 to 4. Okay, and simplifying all this, okay, upper limit minus lower limit, that's 1/2 4 to the 4th power minus 1/6 4 to the 3rd power. Okay, so that is the upper limit minus lower limit, which is 1/2 1 to the 4th power minus 1/6 1 to the 3rd power. Okay, so simplifying all this, well, 4 to the 4th power, okay, so that's 16 squared over 2. Well, I get, according to my notes, I get 128 for the first group of parentheses and negative 32 thirds. Wait, no, that's 128 only for the first number, minus, yes, 32 over 3. And then careful, minus 1/2 minus equals to plus 1/6. And simplifying all this should give us actually a nice integer, 117. Right? So that's what I get on my notes. Also, very important when dealing with double integrals, something I forgot at the very beginning. I forgot to do it at the very beginning. We need to state the domain of integration. The domain of integration using the correct set builder notation. And all we're going to do is use these limits to write that domain of integration. So that'll be all the ordered pairs x, y, such that, well, x is varying between 1 and 4, and y is varying between 0 and x. All right. This is going to be very important for every double and triple integral we will be working, because, well, number one, it's going to give us the limits, and also it's going to describe the region of integration. Well, we're going to get into regions soon, and then, well, it's going to be useful as well when we change these domains into polar and what else, cylindrical, spherical, all the different transformations we're going to do. Yes.
Does it matter if we write first like x or y?
It doesn't matter, but typically we go in alphabetic order, but it's fine. Yep. Mm-hmm. Okay, evaluate, example number 4. Evaluate the integral from -4 to 4 and from 0 to x squared for the function 64 minus x cubed dy dx. Okay. So, number 1, let's establish the domain of integration. Okay, so our domain of integration, all the order pairs x, y, such that, okay, careful because the order is still the same, dy dx. So, x is varying between -4 and 4, and y is varying between 0 and x squared. Okay, so that'll be our domain of integration here. Let me make some space. Okay, so I believe we're ready to integrate this function with respect to y. Notice how the integrand only depends on one single variable, which is x. So it's a constant with respect to y, right? So the integral of this constant with respect to y will be the constant times the variable, which in this case is y. That is the integral from -4 to 4 of the constant square root of 64 minus x cubed times y. Evaluate that between 0 and x squared. Don't forget the dx. Okay? Now, again, keep in mind that these limits of integration only apply for the variable we just integrated with respect to, that is with respect to y. So I will be constantly highlighting this variable so you can see how we go about the work. All right? After a while, you may not need to do all this. All right? So let's see, upper limit minus lower limit. Well, so that's the integral from -4 to 4 of the constant, that is the square root of 64 minus x cubed. Careful, the y is outside of the radical. That is going to be x squared minus 0. I'm not going to write the 0. Well, you know what? Let me write it down just so you can follow where it's coming from. And then that's the integral from -4 to 4 of the square root of 64 minus x cubed times x squared dx. All right? Any ideas how to evaluate this integral? Use substitution, right? Now think about it. What if we were given this integral in the other order of integration? Instead of going dy dx, we had to go dx dy. Did you see how it's not possible to evaluate, or at least not with the tools that we have so far? I mean, there's many advanced integration techniques that we don't learn neither in calculus 1 or calculus 2. So, but it's possible to evaluate an integral like this. Also, those tables of integrals that you see at the end of the calculus books with like 140 formulas, you may find a formula there. Actually, there are books with thousands of integration formula. They're this big actually, and these are books for integrals, series, products, and transforms like the Laplace and Fourier transform. And well, you can use one of those books and maybe find a way to integrate this one. Maybe it's possible, but at least with what we learned in Calc 1 and Calc 2, this one is not possible. All right? Okay, so let's go about the use substitution. So let me change. Let's do 64. U equals to 64 minus x cubed. Du equals to, what's that? -3x squared dx, where x squared dx equals to -1/3 du. All right? I will also change the limits of integration, and in this case, for this particular function, you might want to do it because you don't want to back substitute with these radicals and then write a lot. Just you'll see how this will simplify a lot of our work. So u at -4, that is 64 minus -4 squared. Cubed. Careful with the signs here because -4 cubed is going to be still negative 64 times the negative outside becomes positive. 64 plus 64, 128. And then u of +4, that is 64 minus 4 squared, which is, 4 cubed again, which happens to be 64, which is 0. So what are we going to get? Now that we changed the limits of integration and the variable, that is the integral from 128 to 0 for the function square root of u times -1/3 du. So there's a lot going on here. Number one, the limit of integration, looking weird. How do they look weird? Because we have the lower limit looking that it's larger than the upper limit. That's normal. That happens a lot, very often times when we change the limits of integration. And also, but I mean, if that bothers you one way or another, well, you could do the following. Again, use the negative sign from the du part of the problem. Use it and reverse the order of integration. So number one, I'm going to take the 1/3 outside of the integral, 1/3 integral from 0 to 128. I'm going to change this to u to the 1/2 du. Okay, so this will be 1/3 u to the 3/2 over 3/2. Evaluate that between 0 and 128. Okay, let's simplify this. Okay, dividing by that 3/2 is the same as multiplying by the reciprocal. So 1/3 times 2/3 u to the 3/2, still from 0 to 128. And well, let's multiply these coefficients. Let me continue here. Okay, so that'll be 2 over 9, 2 ninths. U to the 2/3, 3/2, from 0 to 128. That equals 2 ninths, 128 to the 3/2 minus 0 to the 3/2. And we need to simplify this to lowest terms. Okay, yes?
I think it's negative 2 ninths.
Okay, but I use the negative here to reverse the order of the limits of integration. To go from 128 to 0, I changed the limit from 0 to 128 by using the negative sign. How do we do that? Well, let's recall that when one of the properties for integrals, when you have the integral from a to b, that's essentially the same as negative the integral from b to a, right? Okay, so now here we need to go about this. Let's go back to radical notation. So that means, okay, this denominator indicates the index of the radical. That means it's going to be a square root. Now the question here is 128 a perfect square? You said? No. Okay, so then we're going to express it like this: 2 over 9 times the square root of 128 cubed minus 0, which is just minus 0. No, don't cube this number. Don't cube this number. Instead, write this number. That is 128 squared times 128. Break it up so you come up with a perfect square. That is, okay, 128, the square root of 128 squared, well, that's 2 over 9 times 128. And it's going to leave us with 128. Now, yes, the number 128, again, we already discussed, it's not a perfect square. However, if we keep with multiplication, that'll give us, okay, 128 times 2, that's 256 over 9. And then the square root of 128, isn't that 64 times 2? And 64 happens to be a perfect square. The square root of 64, that's 256 over 9 times 8 square root of 2. Simplify this to get 2048 over 9 square root of 2. So we need to simplify these numbers to the lowest possible in terms of simplifying radicals. So not just simplifying fractions to lowest terms, but also the radicals as well. All right? So that was another example of a double integral. So, and again, as we discussed earlier, the inside limits of integration are with respect the inner variable dy, while the outer limits of integration are for the outer variable. Now, here is the thing: for what we want to apply in terms of double integrals, I mean, yeah, applications to like areas of volumes and what else? Mass of a planar lamina and other integrations like surface integral that we're going to do later and surface area as well. So the innermost limits of integration can be simply numbers or variables with respect to the outermost variable, while the outermost limits of integration are only constant values. This to ensure that the final answer for a double or a triple integral will be a constant, a number that means something. Maybe it means an area, maybe it means volume. So, well, we'll see how we're going to distinguish between the different integrals. What makes an integral to describe a volume? What makes an integral to describe area, etc., or mass? I don't know. Okay. Applications of applications of double integrals to find area. Of course, you guys know how to find the area between two curves or under the curve, right? That's simply integrating from A to B under the function that describes that curve. Okay, well, but what is this going to be in this case? Well, let's see. Let me open GeoGebra to show you an animation of how we go about it. All right, well, the old approach to find the area under the curve, what do? Areas between rectangles, right? So, oh no, that's over here. But again, do you see how this is not going to give us the actual area between the two curves in this case? Well, that's because we are chopping our region of integration into a finite number of rectangles. And well, there are spaces that are not considered, but then there's also these areas outside of the region of integration that it's not going to give us a good result. So the solution to the problem is to chop this region of integration so that the delta x is as small as possible, which implies, well, it gets as small as possible, essentially giving us infinitely many of those rectangles. You know, Riemann sums, evaluate the Riemann sum. So we're going to take a very similar approach here. So, but rather than dividing this into rectangles, so we are going to divide this into squares. Let me open the project first. Okay, so all right. So this time, rather than finding the area between two curves, and rather than dividing into rectangles, we're going to divide into square regions. What are those squares going to be? So instead, here we're going to have, here we're going to have these squares where we have some length, let's call that delta x and delta y. That is an increment in the direction of x and an increment in the direction of y. Now, if we increase the number of m's, the number of squares, we get more squares to find the areas of, giving us a better result. So we're getting a more refined region. Well, let me show you the. Okay, let me turn on the lights for a second. Okay, let me give you the 3D perspective. So in essence, we're finding the area of this square region under this under this surface. So if I decrease the number of squares right here, it's not giving us the actual a really good area there. So we're not getting a very good refined area. So in a similar way, that the more rectangles we have under the curve, the better the result. That is infinitely many of those. Same thing here, all right? Same thing with double integrals, all right? So that means if I take, say, this sample square, all right, with length delta x, with length and and width delta y. Okay, so this is going to have an area equals length times width, delta x times delta y. But if we wanted to find the area of the entire region, then we would have to sum. Actually, it's going to be a double Riemann sum with delta x sub I, delta y sub I, where, oh, it's not I, it has to be a different letter. Let me use j, where I from equals 1 to n and j from 1 to m. So we're going to use n lengths and widths. So we're going to fill in this region of integration. And of course, if we take the limit of this double sum as m and n approach infinity, both approach infinity, that's simply going to give us the double integral right here. All right? So, well, and now you might notice, we have two pictures here, right? One where we have a function at the top and one function at the bottom. And then we have this other picture where we have a function to the right and a function to the left. So that's going to depend on the setting we're working on, because here we're going to describe two types of regions. Let's label this type 1 region versus type 2 region. How do we distinguish a type 1 region from type 2 region? By the way, regions can be both type 1 and type 2. So we describe a type 1 region when the region is vertically simple. This is key to set up the double and triple integrals, determining whether the base of the base of the region where we're integrating, it's vertically simple or horizontally simple. Well, what does that mean? That means that if I trace vertical lines, do I always have the G2 at the top of G1? Is this always true? It is. So that means this is vertically simple. But what about the other setting? For type 2 regions are to describe horizontally simple regions. Horizontally simple. That means that if I have h1 and h2, the rightmost function will always be to the right of function 1. Function 2. Well, you know that's 1. Yeah, it's 1. So, and that's how we know this is a horizontally simple function. Okay? So, for instance, what about, okay, let me see if I can make something up. Like this region. Is that region is it a vertically simple region? Okay, so if this is F1 and this is F2, okay. Yes, is it vertically simple? Is F1 always at the top of F2? It's not, right? It's not. I mean, it's vertically simple piecewise, if you will. So in this case, you would have to set up two double integrals, one to calculate this area and another one to calculate this other area right here. Which is what you did back in Calculus 1, but you didn't do it in terms of a double integral. You did it in terms of a single integral. So you'll see the connection once we get to finding these areas. Now, a very important note here. The integrand integrand must be a 1 in order, so for the integral, to describe area. So that is, there must be an invisible 1 in our integrand here. If you have something else like an x, like a 7, just a number, 7 for instance, what else? X squared y, or like the functions we have integrated during today, well then that's no longer an area integral. That's something else that we will discuss. There is actually two possibilities for what that integral represents. Okay, so write an iterated integral to find the area of the rectangle formed by the lines x equals 1, x equals 4, y equals to 2, and y equals to 6. All right, so number 1. This information, it's giving us the region of integration that we're going to call R. Let's call this R. That means all the order pairs x, y that are for which x are in between 1 and 4, that is, x varies between 1 and 4, and y varies between 2 and 6. Okay, so we need to write these domains of integration. Based on these domains of integration, we're good to go and plot these regions of integration. That means, okay, so let's plot. X goes between 1, 2, 3, 4. Y goes between 2 and 6. 1, 2, 3, 4, 5, 6. And so between 1 and 4, that is between 1 and 4, and between 2 and 6. All right? So that's going to give us the region of integration here. So we will shade inside. Make sure to shade. All right? So this is what we're going to call R, our region of integration R, right? Which is what it's stated in as a domain. All right, so we're ready to set up the double integral. So area, which is the double integral over the region R. So before writing down the limits of integration, we write this little r, or sometimes another uppercase letter, typically Q, typically D, typically R, S, well, different letters. So dA, this is in general a way to write down a double integral that represents area. How do we know this represents area? Because there is a 1 in the integral, in the integrand. All right? And in this case, well, although you could go about either dy dx or dx dy, in this case it's not going to matter. Typically we go in descending alphabetic order, dy then dx, or for triple integrals typically we go dz dy dx. So let's go about dy dx. All right, so dy dx, so for the inner limits of integration, notice this is connected to the y variable, and in this case y is varying between 2 and 6, while x is varying between 1 and 4. All right, let's evaluate this double integral to find the area. So that is the integral from 1 to 4, and then while evaluating the integral with respect to y, that's simply y between 2 and 6 dx. Upper limit minus lower limit, that means the integral from 1 to 4, 6 minus 2 dx, that is 4 times the integral from 1 to 4 dx. And lastly, that integral with respect to x, that is 4 times x between 1 and 4. 4 times 4 minus 1, that equals 4 times 3, which equals to 12. All right, which is the same result as if you did it using the formula to find the area of a rectangle, right? Because that is 3 units by 4 units. It's a rectangle. It's a 3 by 4 rectangle. All right, but we're using a double integral to find the area of this. Okay, let's see. Okay, yeah, we have time. Use an iterated integral to find the area enclosed by y equals 4 minus x squared and y equals to x plus 2. It looks exactly the same problem you did back in Calculus 1, but we're going to use Calculus 3 to solve this problem in a different way. All right? So let's graph first of all. All right, let's graph. Yes, so number 1. Oops. Yes. So, so that is 1, 2, 3, and 4. 2, 3, and 4. So what do we have? This diagonal line with a slope of 1 and a y-intercept at 2. That means it's going to cross these 2 points. Okay? Well, roughly. Okay, that's going to give us this line right here. And the parabola 4 minus x squared with intercepts at plus and minus 2, going all the way up to 4. Okay, that's going to be this parabola. And I'm going to do it the other way. It's not working the way I was expecting. Much better this way. All right. So like this. What are we doing here? Okay, number 1, let's shade our region of integration, which is going to be this. That's the area they're asking us to calculate, right? So what do we have? Number 1, area, which is the double integral over the region R dA. This dA again will be either dy dx or dx dy, depending on the order of integration we go about. So number 1, here is where we need to analyze this region. Number 1, is this region vertically simple? That is, do we have the parabola always at the top of the diagonal line within the interval that we're looking at? It is, right? Is it horizontally simple? What do you think about horizontally simple? Yes, you say yes. So that is, do you have the same function always to the right and the same function always to the left? Not in this case, right? So if you were to take the other direction, say you want, so in this case clearly it's vertically simple, but over here, if you wanted to take the horizontally simple, here, well, what do we have? The diagonal line to the right and the parabola to the left. But then we're going to this, we're getting to this point where it's no longer the diagonal line to the right. It's rather half of the parabola, and then the other side, the other half of the parabola to the right. So that makes it not horizontally simple. What would you have to do? Set up 2 double integrals, and well, you don't want to set up 2 double integrals, and also I don't think you want to solve those equations and get them in terms of y. No, you don't want to do that. All right, so let's keep it horizontal, vertically simple instead. Okay, that means this is the integral, okay, dA, which is dy dx. So the upper limit, which is 4 minus x squared, the lower limit, which is x plus 2. Oh, but what about the outermost limits of integration? We need to figure them out on our own. That means we need to find this intersection points between the parabola and the diagonal line. I'm going to do that algebraically on the side. So that is, oh, actually, let me leave some room right here for the domain of integration. So that is, let's set x plus 2 equals to 4 minus x squared to get those intersection points. So because this is a quadratic equation, let's move everything to the left hand side. That is x squared plus x plus 2 minus 4. Set it equal to 0. Combine like terms. X squared plus x. 2 minus 4 is that negative 2. Set it equal to 0. This polynomial is relatively simple to factor. So factors of negative 2 that add up to, what's that? Add up to 1. Those are plus 2 and negative 1, right? This means x equals to negative 2, which is actually this point right here, and x equals to 1, which is this x equals to 1, right? So those are our limits of integration. So we're going to go between negative 2 and 1. With all this said, we're ready to write our domain of integration. That is, x is varying between negative 2 and 1, while y is varying between x plus 2 and 4 minus x squared. Let's evaluate this integral. Okay, the integral with respect to y, that's the integral between negative 2 and 1 of y between x plus 2 and 4 minus x squared dx. What are we going to do? Upper limit minus lower limit. Okay, upper limit minus lower limit. That is the integral between negative 2 and 1, and that is 4 minus x squared minus x plus 2. Hold on, doesn't that look like what you did in Calc 1 or Calc 2, depending on where you learned this? Upper function minus lower function? That's how we set up the area integrals in Calc 1 and 2, right? Well, so really what you learn in Calc 1 or 2 is the result of doing Calc 3. But in Calc 3, we're generalizing the idea to start with a simple region that is vertically or horizontally simple, and then from there set it up as an iterated integral. Well, this is going to be the integral from negative 2 to 1 of negative x squared plus 4 minus x minus 2 dx. And simplifying this, that's going to give us the integral from negative 2 to 1, that is negative x squared minus x plus 2 with respect x. And well, I'm going to skip the integration here and the upper limit minus lower limit. I think you guys know what this is about, right? So just integrate each term, upper limit minus lower limit, fundamental theorem. That is going to give us a result of 9/2 units, right? Could be centimeters squared, could be inches squared, depending on the scale or the application we're applying this to. All right, so that's how we apply double integrals to find areas between two curves. Let's have a look at a very important theorem that we may be using a lot. Okay, so the next theorem, which is about rectangular region. How do we know our region is rectangular? That's when we have this kind of domain and both x and y are limits that are constant. If we have like an x square, it's no longer a square region, a rectangular region. And we can simply use what we call Fubini's theorem. But what is that? We can simply interchange the limits of integration without having to do anything with the functions that describe that region. That's something we're going to do when we don't have this constant value. So example number 7 is to see this theorem in action by rewriting the integral in example number 5 by reversing the order of integration. So what did we have for example number 5? We started with the integral from 1 to 4, and what's next from 2 to 6 for dy dx. That equals um, just reverse the order. Instead of going from 1 to 4 and from 2 to 6, go from 2 to 6 and then from 1 to 4. dx, dy. Change dy dx for a dy dx. And I'm not going to evaluate this double integral because it should give us the same result. Alright? I mean, it's not hard to evaluate anyway. X from 1 to 4, that's 3. And then y from 2 to 6, that's 6 minus 2 equals to 4. 4 times 3, 12 again. Alright? Okay, so what's the next exercise? The next exercise, example number 8, that's a good example in which we are going to change the order of integration, and we will also come up with functions of y to reverse the order as well for the limits of integration. However, let's take a break and then come back to this later.